Hi, Dr. Anthony Revis here with Watch Me Work It. Few gas law problems. All the gas law problems for the most part work the same. You just plug in the formulas. That's it. If you could do one, you could do them all. And the way you'll know which one it is just simply by marking it up. Okay. What is the decrease in temperature? So here we're looking for T is in question. When 6.00 liters, so that's a volume, at this temperature, at 20.0 degrees C is compressed to a second volume. So this is T2 that I'm looking for. And when I see V's and T's, I know that's Boyle's law. So I set it up as V1 over T1. The T's always on the bottom of these equations. V2 over T2. When I see this, I simply write it all out. And I'm looking for T2. What I could do now is simply put in the values and let the calculator do the rest of the work. I really suggest that you follow this way. So let's put in V1 and T1. So T1 is 20 degrees C plus 273 automatically to get this to K. So that's 293 K, always K. So the first thing I would do on my paper, as soon as I see it, I would do the plus 273. And so here, this is going to be 293 K equals V2, which is 4.0 liters. They're in the same unit, so that works really nice, over T2. I would do this, and then I would let my calculator do the rest of the work. Okay, for those who struggle a little bit sometimes with the math. All right. So once you set that up, T2, then we'll punch out in your calculator as 195.3 K. And occasionally with temperature, people tend to omit sig figs. But if you want to put this to sig figs, then you would simply notice there are 3, and this will be 195 K. Temperature is one of the areas where sig figs are lag behind. Okay. So that's how we do it. Simply put it in the formula and you punch it through. Okay. And you can mark up your paper that way. You'll know what you're doing. Let's do another one here with the ideal gas law. I've already told you it's gas law, but you would discover it from marking it up. We have 7.7. If I have 7.7 moles, so that's going to be N of gas at a pressure of that number ATM. That's pressure, and at a temperature of 56 C. So right away, I see that's 56 C. So I'm going to go ahead and tell you what, I'm going to change that temperature right away, plus 273, so I can keep my eye on it and won't lose. And that way I won't lose track of what that temperature um, should really be. Okay. So I have that, and that's going to, if I add it up, I can go ahead and do that now. 293 K. What is the volume? So we have volume in question of the container of that gas. Now the volume of the container is the same as the volume of the gas. Okay, that means the same thing. So here I see my PV equals nRT because this is a constant which I can get from a table, and everything else I see is a variable in the equation. I see N, P, and V. So I'm going to just take this then, and now you can rearrange this, or you could just put all the values in. We have our pressure at 0.09 ATM, and make sure when you do this that you use standards that have the same units. Did I put it wrong? Yeah, there we go. Nope, wrong number. 0.9. No, we're okay there. Um, ATM times our volume. The volume that we have here is what we're looking for, I think. So we're looking for V2. So we'll just write that again. So let's do this. Let's erase this and start a little bit cleaner than that, so we could see it a little better. That's all. So let's rewrite it here a little neater. That's possible for me. 09 ATM. And we're looking for volume. So we'll just write V there. We have the moles given at 7.7 mole. And we have R, which is a universal gas constant that we look up on a table, and that value is 0.0821. Okay, liter dot ATM per mole. Okay, and that's time. Really didn't do a good enough job here writing this out. Times T, which is 2. We'll squeeze it in here. 329. Okay. If you permit me, I want to rewrite that for you a little neater again. 0.09 ATM. Ran out of room over there. Times our volume. 7.7 moles. 0.0821 liter atmosphere per mole dot K times the temperature of 329K. And then we just solve for B. Punch that through in your calculator, and you're going to get a number that looks something like 2310.93 liters. And so here, if we have, look like we have 1 sig fig. So this gets to discretion of whether you're following sig figs or not. So we get 1 sig fig, that will be 2,000 liters. Okay. All right. So there we have that. And so that's how you do that one. Let's just do one more here. A sample of neon has a volume of 78.8 liters at STP. Calculate the number of grams. STP is standard temperature and pressure. Standard temperature is 0C, which is 273 K, and it's 22.4 liter per mole at 1 atmosphere. So in this particular case, this is a dimensional analysis that we could carry out here because we have 75.8 liters. And so that's liters, and it's only one species, so we don't have to worry about tracking that through. So that's going to be liters that we could take to mole, because we're looking for gram. I'll write it out here so I can keep an eye on a gram. So I'm looking for. So this is going to be 22.4 liters in every 1 mole because it said at STP. So this will be times mole. And we're dealing with what? Neon. So per gram of neon, and all these are neon. And so the grams per mole of neon is from the periodic table is 20.18 over 1 mole. If we punch that through on a calculator, we get 68.2876. And so the normal sig figs here is going to be 3. So 68.3. And this was grams. And this is grams is what I'm going to square in as my final answer. Okay. And that's how we do that one. Okay.